Welcome back everyone. In today's video, I'll be explaining problem F from the AtCoder Beginner Contest 318. I've provided the correct Python code in the video description, so please look after you've listened to my explanation. Let's start with the problem statement. We have n items on the x-axis. They are labeled with numbers from 1 to n and located at xi. We first choose an initial position x equals k and do n determined steps. At the ith step, we are given the width li and we can get an item within the distance li from the initial position we chose. We can't get more than one item at once. Our target is to get to all the n items after n steps. The question is to find the number of cases choosing an initial position to get all the items. Here's an example of the problem and a successful case with k equals -3. In that case, we will get x2's item, x1's item, and x3's item in the order. Let's proceed with solving the problem. Firstly, we examine the example. Let's consider the last step and we think about what initial position realizes the last step. Notice that the width increases as the step increases. So we conclude that we never get the item which can be reached at the last step. This means that the range of the last step from k minus L3 to k plus L3 must include all the three items. So we have three inequalities here, and we can put them together like this. The inequality in red ink is a necessary condition for the last step. We extend the idea for each step, and we would like to get other necessary conditions. Here, I introduce that of step 2 in the example. At step 2, the range must include at least two items. So it's necessary to have consecutive two items at least. So we have a case of containing x1 and x2 and a case of containing x2 and x3. We calculate them in the same way and get two intervals. Then, since satisfying either of them is sufficient to achieve step 2, the union of them is a necessary condition for step 2. We apply this idea to each step and we have n necessary conditions in total. Note that they are only necessities, but here it's worth thinking about the x-coordinates which satisfy all the conditions. That is, when we start with x equals k satisfying every condition, we pass all the steps and we can get all the items. That's because for each step I, the condition sets we have at least I items in the target range, and we have selected I-1 items by step I-1, so at least one item is remaining in it. Therefore, the intersection of n necessary conditions satisfies the sufficiency of the problem, so it's precisely the target condition of the problem. Now, let's briefly review what to do. First, prepare n number lines to record n necessary conditions, and then check all the consecutive items and record the conditions separately by step. Finally, taking the intersection of the n lines, that's the summary. Okay, let's introduce the algorithm. We define cube of I and j as the number of intervals including x equals j for step I. Here, cube of I should be regarded as a number line for step I and index j as x coordinate. Then check all the pairs L and R satisfying between I and n. A pair L and R means the consecutive items from XL to XR. We define I as the number of consecutive items, and it also means a condition about step I. We have I inequalities from a pair L and R, but we can put them together as red ink. Then we record the information about the interval in cube of I as follows. After checking all the pairs R, L, and R, we take cumulative sum for each number line cube of I. We finished getting n necessary conditions. Now we start to take the intersection. For each j, we should check if cube of I and j is greater than 0 for all I, because that cube of I and j is positive means that it has at least one cover of intervals. In the diagram of cube, we can check it to see the diagram vertically. Finally, the number of such j's is the answer to the problem. This is the outline of the algorithm. However, we can't pass it with this algorithm. Why? The size of cube of I and j may be enormous because the index j represents x coordinate, and it might be so large. So the last thing we must do is to compress coordinates. Let's count the number of x coordinates to implement the algorithm. For each L and R, we like to add at most 3 coordinates. Therefore, the total number of required coordinates is at most 3 times n squared. So, after compressed, the size of cube of I and j is at most 3 times n cubed, which is about 10 to the 7th and acceptable. With that, I've completed the explanation. If you have any questions about the problem or any requests for solving other ABC problems, please feel free to comment. Thank you for watching the video.